In a previous video, we looked at the idea that the determinant of a matrix product was equal to the product of the determinants of the two individual matrices. So we have that the determinant of the product AB, where AB is a new matrix, is equal to the determinant of A by itself times the determinant of B by itself. What happens if if the two matrices that we're talking about are not A and some generic random matrix B, but the matrix that's the inverse of matrix A? Well, in that case, we have that A and A inverse are still two different matrices, so we have the determinant of A times the determinant of A inverse. But A inverse, that matrix, is just the identity matrix. And so what we're saying here is that the determinant of an identity matrix is equal to the determinant of A times the determinant of A inverse. Well, what's the determinant of an identity matrix? An identity matrix looks like this, where all the entries on the diagonal are 1, and all the other entries are 0, so it's a triangular matrix. Therefore, the determinant of this matrix is equal to the product of the values on the diagonal, which is 1, no matter the size of the matrix. Now, this is a square matrix because we can't take a determinant unless it is. But the determinant of any identity matrix is 1. So we now know that the determinant of A times the determinant of A inverse is equal to 1. Since this product, this is a number and this is a number, and this product is equal to 1, then we know neither one of these is 0. If either one of these was 0, then the product of these two values could not equal 1. All of this is contingent on the fact that A has an inverse. It might not, but if it does, then we can say that the determinant of A is not 0 and the determinant of A inverse is not 0. The important takeaway from this is if A has an inverse, then the determinant of A is not 0. This statement says that if A has an inverse, then the determinant of that matrix is non-zero. And it's important that you recognize that the order of that statement is very important. It does not necessarily mean that the determinant of a matrix turning out to be non-zero implies that that matrix has an inverse. As it happens, it is true in both directions, but you have to be careful when you write a statement like this that the order of the if and then parts of the statement are taken into consideration. Let's take a look at what we call the converse of this statement. If the determinant of a matrix is not 0, then that matrix has an inverse. I'm going to take matrix A and I'm going to perform elementary row operations on it, and I'm going to represent those elementary row operations by elementary matrices. I'm going to do this as many times as is necessary, we'll call it k times, until I get to a reduced echelon form of the matrix. What I have here is a product of matrices. So if I take the determinant of my left-hand side, the determinant of R, that's going to be equal to the determinant of this matrix, which is a product of matrices. And we now know something about the products of matrices, right? The determinant of a product is the product of the determinants. So I can take the determinant of e to the k, multiply it by e to the k minus 1, multiply that by the determinant of, and so on, down to the determinant of e to the 1. Move this over a little bit. I don't want to move the whole thing. And that's times the determinant of A. And all I've done here is break this determinant of a product up into the product of determinants. Okay, I've taken the determinant of the left-hand side, the determinant of the matrix R, and the determinant of the matrix on the right-hand side, and split that up into the product of determinants. So I moved this over, so it's a little harder to see now, but this determinant of R is equal to this determinant, which in turn is equal to this product of determinants. Well, the nice thing about this is that every elementary matrix is invertible. We established that quite some time ago. So we know that the determinant, we know that the matrix E sub k has an inverse. And we know that the matrix, the next one down from E sub k minus 1, we know that one has an inverse, and E sub k minus 2, all the way down to E sub 2 and E sub 1. These all have inverses. So we know, we may not know what these values are, but we know they are not 0 because of this result that we got earlier. So all the way down to here, we know these are not 0. All right, I'm going to take this string of determinants of elementary matrices, each one of which we know is not 0. I'm going to multiply them all together. They're just numbers, but they're not 0. And I'm going to call that number n, just so that we are not distracted by what we need to do next. The point I need to make here is that each one of these elementary matrices has an inverse. Because it has an inverse, its determinant is not 0. This product is made up completely of non-zero numbers, so this highlighted product here is not 0. It's some number n that is not 0. Okay, so since this is not 0, as long as the determinant of A is not 0, then the determinant of R is not 0. Well, R is just the reduced echelon form of A. It's possible for a matrix to have a determinant of 0, but if it's in reduced echelon form and it has a determinant of 0, then that implies that there is a row that's all zeros. One of the rows of the matrix is all zeros. And since the determinant of A is not 0, that implies that the determinant of R is not 0. Since R is in reduced echelon form, there are no non-zero rows in the matrix R. Well, if you go all the way back to Theorem 2.6.3, the invertible matrix theorem, we know from that if you can perform elementary row operations on a matrix, and by doing so turn it into an n by n identity matrix, if you can do that to a matrix, then that means that that matrix is invertible. That's one of the things the invertible matrix theorem says. So what that tells us essentially is that the matrix A has an inverse. So what I've just shown, very informally really, is that if the determinant of a matrix is not 0, then that matrix has an inverse. Over here we show that if a matrix has an inverse, then the determinant of that matrix is not 0. And so we'll write that statement in a single sentence rather than two separate statements. A is invertible, an invertible matrix. That's one side. The other side is the determinant of A is not equal to 0. And in between, I'm going to write IFF, which stands for if and only if. And you might also see that as a bidirectional double arrow. The importance of this symbol or this phrase is that it doesn't matter whether you know that A is invertible. From that, you can make the claim safely that the determinant is non-zero, or whether what you know is that the determinant of some matrix is not 0, some square matrix. If that's the case, then you know you can find an inverse, or at least that an inverse exists. Let's take a look at a quick example. Let's find out if A has an inverse. We're not going to try to find that inverse if it exists at this point. We're just going to try to determine whether it has one or not. all we need to do is figure out whether or not the determinant of A is equal to 0. If it is, A does not have an inverse. If it's not, it does. And that's it. That's all we need to do. So how do we find the inverse of a 3 by 3 matrix? Well, we pick a row or a column. It's convenient for us to expand on, and I think I'm going to use this one. And we perform cofactor expansion on that row. So I'm going to have 1 times, let's see, I need to cross out the row and the column that 1 came from. That leaves me with a submatrix, and the determinant of that submatrix is 0 times 3 minus -1 times -1. So I have 1 times -1, which is -1, and that is not 0. So A is invertible. And that's it. Now, there will be times when we want to find the inverse of a matrix once we know it has an inverse, but that's actually the next subsection title, so I'll save that for the next video.